Good morning, everyone. Thank you for joining us today for Calculating Energy Costs webinar. We want to thank the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance for their support in co-sponsoring this series of free energy efficiency trainings that are open to all Northwest utilities and their customers. My name is Beth, and I will be hosting today's webinar, which means I'll be monitoring chat and conducting some polling at the end of the webinar. Before I introduce today's presenter, I'd like to show you some of the tools you'll be using during the webinar today. To the right of your screen, you'll see several windows: the participants window at the top, then the chat window, and the polling window, which will appear at the end of the session. If you have any questions during the webinar, you can submit them to me through chat, and to me, the host, through chat, and the instructor will answer them at the end of the webinar. Since this will be an informal session today, if you'd like to share an example or you have a question you'd like the instructor to address immediately, please feel free to use the raise your hand icon at the bottom of the participants window. At the top left corner of the screen, beneath the Quick Start tab, you'll see some annotating tools, which I will show you here in this slide. You'll see some annotating tools, including an arrow, a marker, and a text tool. The presenter will ask you to use these on specific slides, so you don't need to worry about them until he references them. Now I'd like to introduce today's presenter. John McLean is a Training and Education Project Manager with PGE. John has over 42 years of wide-ranging experience, including distribution, field operations, information systems, corporate planning, budget, and energy efficiency programs. He holds a BS in Business Administration and an MBA in Organizational Effectiveness. John is also an adjunct faculty member at Clackamas Community College and teaches several classes as part of the Energy and Resource Management program. John is also an adjunct faculty at Marylhurst University, where he teaches several courses as part of the MBA in Sustainability program. So now, without further ado, I would like to hand the webinar over to John. John?
Thank you, Beth. Well, good morning, everybody. We're excited to be here. The forecast here in Portland was for freezing rain, but it didn't happen. So wherever you're at from around the Northwest, I hope you're having as good a weather as we are. A little cold, but dry. So today we're going to talk about measuring electricity, calculating energy savings for projects, a little examples there. How do I evaluate a simple project evaluation, some of the simple decision making that goes on that we find with our customers. And then at the end, of course, where do we call to get advice and help, either from your local utility, PGE, Energy Trust of Oregon, and the Northwest Energy Efficiency Alliance has some programs out there too. So lots of people ready to help you. Looking at the list of people here today, we have directors, finance, energy planners, business analysts, facilities people, presidents, founders, a very good representation of customers in any community that kind of want to get it started with how do I manage this thing called energy, electricity specifically, and we're going to talk about some of the simple tools today. But first, why we start with this one each year. It is all about what gets measured, gets managed, quote from Peter Drucker, but it's still very true today. The minute you start measuring something and people know you're measuring it, suddenly it is important and positive things will happen. So this is what we're applying to electricity. It all starts with what gets measured gets managed. Second paradigm is there is the plan, do, check, act, the management cycle that is very common in energy management. And measuring ends up in two of those, planning, developing baselines, where do we start, what do we expect to happen. And then, of course, once you do implement a measure, then you can monitor it, measure it, audit it, take corrective actions. Gee, that didn't work the way we thought. All those require some simple understanding of electricity and its characteristics. So with that overview, let's get started in some of the simple measurements. There is something called Ohms Law, We won't talk about that today, but we will pick out a few pieces of Ohm's Law that you will see on your electric bills and around your offices and buildings. So let's talk about the amount of force or potential applied. That is the mighty volt. And if you, one of the most common ways that they teach about electricity is pressure, and they use water hoses out in the front yard or the water pressure around your house. And as you know, if you're trying to take a shower and everybody's sprinkler system suddenly went on in the morning, you might have less water pressure than you like at that shower head. That is the amount of force, the potential, the pressure. And just like electricity, you can have volts without much going on, just like you have 60, 80 pounds of pressure per square inch in your water system. You can have voltage at any time. When we talk about power, you then talk about amps. It's the volume. The amount of electrons flowing through a conductor is similar to the gallons per minute going through the water hose. And of course, you know that if you have a big Rainbird sprinkler head out there, you need a bigger size hose to give it the water it needs to work. So you can go to the store and have a 1/2 inch hose, 3/4, 1 inch hoses. So the size of the hose is the volume of water. The same thing is true of electricity. The bigger the wire, the more electrons that can flow through it. This can drive up costs, of course, by, bigger the wire. If it's copper, it's going to be pretty expensive. So we'll talk a little bit about how amps is a good measurement that can save you money. And of course, on your bill, you pay for watts. A watt is the volts times the amps. This is for single phase residential, and most commercial run off of single phase, your lighting systems. What's interesting here is you can have high volt, low amps. You could have low volts and high amps. But the watt is the measurement of power. I'll have a couple of terms here for you. We won't get into them today, but a lot of larger commercial and industrial customers have what's called three-phase power. And once you go to three-phase, then it's volts times amps times the square root of 3, and something called a power factor. If you have a lot of motors, industrial process type operations, there will be something called the power factor. For us today, we're going to assume the power factor is always 1, perfect, and anything times 1 is itself. But larger industrial and a lot of equipment would have 0.8, 0.7, something less than 1, and that significantly affects the amount of power that your facility needs. There's also something called the ohm. However, I've never in my career know that customers call and say, man, I've got an ohms problem. But ohm is the resistance of flow. If you get into electronics, you would see ohms and hear about it. But for today, for simple measurements and most decision making, ohms is not part of the discussion. So on your bill, at least in our service area, about 90% of your bill is going to be the mighty kWh. You might also have some demand charges and other kinds of charges on your bill, but most of the cost of your energy use is going to be measured in kilowatt hours. A lot of acronyms are interesting. Here we have the Trailblazers. That's the NBA, National Basketball Association. So here's an acronym that stands for one thing, one association. But kWh is really a laminate of 3 things laminated together. So to understand it, you really need to break it apart. So we get to go back to our high school math class and go, oh my gosh, it is, in fact, the metric system. So K simply means 1,000. You could see an MWH. You could see a GWH. So all the first part of the acronym stands for is how many zeros do we want to play with here today? Do we want to play with 3 zeros, 6 zeros, 9 zeros? If we're talking about a state, if you read the newspapers and talk about major power plants, you're probably going to see the G is the most common metric used there. So whatever number they say, if they say 1, then it's going to be 1 with 9 zeros if it's a GW. The middle part is the electricity measurements we've heard today, the volts, the amps, and the watt. In this case, it's a kWh, and that's the unit of measure for the power. But if you're talking about voltage and you have your own substation for a large industrial plant or some commercial, you might hear someone say, oh, we have kV, which would be 1,000 volts. Occasionally, you would see amps in the same way. And the third part of that acronym is the unit of time, which how many hours. Occasionally, you'll see an A, which means annual. If you work with this budgets a lot, you'll know that there's 8,760 hours in a year. It's 365 days times 24. And so if you have a light that is on all the time, like an exit light, it's on for 8,760 hours a year times however many watts that light has. And you divide by 1,000, you'd get kWh. And we'll have some examples of that. So think of this acronym as a three-part acronym. Could be kWh, kV, could be a lot of different characteristics. It's three things laminated together. So the simple formula for calculating the energy component is you take the watts. You'll find that by federal code. It has to be on the box. It has to be on the equipment. It's the label. So everything comes with watts labels, usually. We divide by 1,000 to get the K involved, and then times the hours of use. One way to think about this is when you purchase the equipment, you've already locked in the W. So efficiency is really important in the purchasing decision. Obviously, the most common example, and we'll have one, is the incandescent light bulb compared to the compact fluorescent. The minute you buy the bulb, you've locked in the watts and for the next life of that particular piece of equipment. The hours is probably the most overlooked element of measuring power. Is people really don't understand how many hours a particular piece of equipment is on or being used. Watts divided by 1,000 times the number of hours gets you your kWh. In this little example, we have 20 light bulbs at 100 watts. Then you'd have 20 times 100 is 2,000 watts. Divide by 1,000 times 1 hour, 2 kWh. Another way to think about this is because the equipment is locked in with the watts when you purchase it, your energy use is a function of renting power by the hour. The more hours it's on, the more you pay. And this is what a lot of people talk about. When you leave the room, turn the lights off. So let's take a quick example here. This is where we can get to practice our, go to the upper left-hand corner, grab your arrow, and I can put that arrow, he said confidently, there it is. I can put my arrow, and every time I click, I can move it around the screen. And here's our example. I'd like you to help me answer this question. How many kWh are used by a 60-watt light bulb 10 hours per day for the next 30 days? So this is a typical example of how much a month does it cost me for a particular piece of equipment or a building or anything that you know the watts of. Of course, the hint is easy. Watts divided by 1,000 times hours. So let's try to answer this. Very good. Some people are multitasking, listening and doing some math. Oh, good. Some people have figured out how to use some of the other tools. Of course, it's really going to be very hard to purchase incandescent bulbs in the future since they are not going to be able to meet the efficiency standards. And most of you have got it right. You have 60 watts divided by 1,000 times 300 hours would get you 18 kilowatt hours. So let's change this a little bit. What if it's a compact fluorescent, which would only use 18 watts? And now let's try to answer that question again. This is more typical. One hint that I like to do, people say, well, I'm not sure it really lasts that long. Mark every bulb with the date purchased, and most places you buy bulbs, if it's within a year or whatever their guarantee is, you can take it back and they will replace it. And of course, the math changes pretty easily down to 18 watts divided by 1,000 times 300 would get you to about 5.4. So this math isn't that tough. Once you know the W, once you've figured out how many hours, and then you can either use a billing period of 30 days or the whole year. That was simple. Let's look at my next question. It's kind of fun. I find electricity measurement is everywhere. And so when you go to the movies, it's everywhere. And so here's a hint. I'm thinking of a movie. The answer is, let's see, 100 million, 1,210 million watts is the answer. And I'm looking for people to kind of think, in what movie would you see that as a electricity measurement? Of course, my next hint would be this particular piece of equipment. And of course, it was the question that Doc Brown asked in Back to the Future of where in the heck am I going to get 1.21 gigawatts, which is the amount of, on the label for this time machine DeLorean, you'd see the wattage on there would be 1,210 million watts. The question now is, what would it cost? How much energy would it use? How many kWh does it take to charge this electric vehicle in 1 second? Of course, the math then would be the formula we already have. You take the 1,210 million, you divide by 1,000. The number of hours in this case is 1/3600th of an hour. So you can calculate that every trip you make with this time machine, it would take 336 kilowatt hours. If you're keep the math simple, if it's 10 cents a kilowatt hour, then that's $33.60 for every trip you make. Pretty efficient transportation. One way just to show how it can be used everywhere to have answer the questions. Power in tons and horsepower. Sometimes it won't be wattage. You will have someone talk to you about, oh, we have to replace a certain air conditioner or refrigeration unit. That can be converted to watts. And likewise with motors, you're buying 550. If you're a water treatment plant, it might be 500 horsepower. But those are also terms that immediately convert to watts. In this case, this is one of my favorite examples of watch out for the efficiency ratings, because efficiency of this kind of equipment is critical. So I like to have financial people. I'd love to have a whole group of purchasing managers, because quite often if you have a facility that has to be operating all the time, things break in the night or break on the weekend, you have to run out and buy a piece of equipment. And I have one business manager told me, wow, they came in and said, wow, boss, we had this 5-ton unit fail on us, and we went out and found a really good deal on a 5-ton unit. Aren't you happy? And the boss knew a little bit and said, what was the efficiency rating? Now, the EER in this example right here is energy efficiency rating. And a higher number means it's more efficient. And sure enough, when you run the math here to figure out a 5-ton unit is either 6,000 watts or it's 4286, depending on that efficiency rating, then you just locked in for the next 12 to 15 years 6,000 watts instead of 4286. So run those numbers very carefully on the purchasing side. The little formulas I've shown you today are very useful. This is a great little cheat sheet to kind of get that controlled. I had one business manager do a very good job of saying they went around with a label maker and all the pieces of equipment. They put on there, here are the specs. If you have to replace this in the middle of the night or on a weekend or whatever, make sure the efficiency rating was at least this when you replace this unit. I thought that was a really good idea. Horsepower, the same thing. If you buy motors, most of them now are getting very, very efficient. But again, watch out for the efficiency rating. If someone offers you a really good deal on a used motor, check the efficiency rating. Again, you would lock in for 10, 15 years a higher wattage than you might be happy with. Quite often, businesses, the capital budget is split from the O&M budget. So the person who pays the electric bills doesn't have a whole lot of influence on the purchasing decision. But I highly recommend you get the two together. In this case, the air conditioner, if you take the 6,000 watts and divide by the 4286, you're going to get that the more efficient is 40% more efficient in your monthly bills. For the horsepower, again, it's 5% more efficient or 5% less bills from the motors. So this is a good little sheet to have start up a discussion. How about circuits? Amps, I've had business people and even utility people say amps are free. Well, they aren't free if you're on the business side. In this case, this is a great example. Again, we do a lot of listening to our customers. They give me the best situations that they were facing. Customers expanding their facilities, wanted to add a 60 horsepower motor, and it was kind of the opposite side of the plant from where the service was, where that was connected to the utility. Both were 60 horsepower motors, both 48,000 watts, same efficiencies. One was a 480 volt motor and the other one was 240 volt motor. Now they both have the same watts, so the bill might look alike, but if you do the math and go 480 volts times 100 amps for your 48,000 watts, or 240 volts at 200 amps. So both provide the same horsepower, the same watts, same bill, but one has twice the voltage the other does. Remember, we talked about the size of the hose being equivalent to more amps, more gallons, I need a bigger hose or bigger wire. Well, if that's copper wire, which it usually is, you need wire twice as large to carry the 200 amps as the 100 amps. Bigger wire leads to bigger installation costs, and the bigger the wire, the more line losses. We won't talk about line losses today, but I assure you that the bigger the wire, the more amps you have, the bigger the line loss through that wire. Very small, but it can add up. Again, if it's something that's running a lot of hours during the year, that can make a big difference. So in this case, they found that they could really cut the total installation costs by not just the efficiency of the motor, but by, again, picking one with a higher amperage, a higher voltage, so they could lower the amps. So there is a hidden cost that's not on the bill of raising the voltages or lowering voltages. So don't buy the 60 horsepower the 60 horsepower motor on a sale just because it's 240 volts, if that in fact isn't going to be made up by the installation costs. So here's a nice sheet that has evolved. I've found that some people love algebra, just give me the formula and I can calculate, and others go, no, break it down into step 1, step 2, step 3. This is a nice sheet you could print out and put on the wall somewhere. It has both. To compute energy costs, find the W, find the label. If you don't have a label, maybe an electrician or someone can help you with volts and amps to come up with the watts. The minute you have watts, then you can divide by 1,000 to get to k-watts. There's a kW, so you can say this is a 5 kW or a 10 kW device. Then you add the H. How many hours is this particular piece of equipment going to be used? And once you have that, kWh, now you can take it times the price. In our service area, it's about 8 cents for commercial. So you'd have a watts divided by 1,000, the algebra formula at the bottom, times the hours, times the price. Now you've got the cost of that particular piece of equipment. So let's do some math examples. Grab your mouse, grab your arrow up the top left corner or whatever marker you want to use. What are the power costs for lighting this office area each month? Lighting is one of the easiest projects to analyze and to see savings. It usually has a pretty quick payback. In this case, the area has 40 different fixtures. Each fixture has 2 lamps, uses 90 watts. The lights are on 10 hours a day, 7 days a week. 8 cents is the price, and you consume 30 days in a month. So get your calculators out. Help me figure this one out. Other projects I've seen while you're doing that are, again, if I'm adding equipment to my facility and you're adding lines and circuits, the electrician may come to you and say, we're out of space in the panel. I need more amps room in the service. And they have found that by changing out lighting and doing energy efficiency projects, they reduce their energy, which reduces their amps, frees up space, and can be a very effective way of avoiding installation costs that are amp related. So here's my answer. The watts here is 40 fixtures at 90. Divide by 1,000 times 10 hours a day for 30 days times 8 cents, it'd be $86.40. I see we have all 3 answers available to us today. And Beth, you're going to send out the slides with the answers. Is that correct?
Yes, I'll be doing that a couple days after the webinar. We'll be sending everybody a PDF of the slides as well as the recording.
Perfect. Good. Well, here's another example. In this case, I want to expand the math a little bit to talk about payback period. It is the most common way that initial decisions are made. Quite often, those are followed up with more sophisticated internal rate of return or net present values. But it all starts with a rule of thumb of how many years will it take to get my money back if I buy that more efficient piece of equipment that John's talking about. So in this case, there are choices between 2 air conditioner units. They have the same exact capacity. Remember, capacity is in tons there. One uses 1,200 watts. The other one uses 1,000 watts. Well, of course, we'd like the 1,000-watt unit because it lowers our energy bills over the next 10 to 15 years. But it costs me $100 more. The air conditioners use 6 hours a day for 4 months, assuming 30 days a month. The cost is 10 cents. I picked 10 cents because we can do the math in our head. How many years will it take to pay back the $100? So in this case, I'm going to do this along with you. The first question is, how many watts are we talking about? I'm trying to calculate savings here. So savings is the 1,200-watt unit minus the 1,000-watt unit. 200 watts of energy savings. I divide by 1,000, so I have 0.2 kW is the savings for every hour this piece of equipment is in use. How many hours? Well, it's 4 months each year, 30 days a month, 6 hours. I get 720 hours in my budget year for this piece of equipment. If I take the 720 times the 0.2 times the 10 cents, I save $14.40 each year. Now I can answer the question, well, how long does it take to get my $100 back? Well, it takes about 6.9 years before I get that money back. Now, if the equipment lasts longer than that, for every year afterwards, then that money is coming in as a improvement to your budget bottom line. But most businesses I've heard and talked to, 5 years is probably the longest one I've heard on payback period. And if you're a restaurant or something, it might be 2 years or even measured in months. So your business usually has some kind, and your industry has some kind of rule of thumb. If it's a program that sometimes the agencies, the departments of energy or the Energy Trust or others might use a 10-year payback because they can take a longer-term perspective. But this is why we have rebates. So my question would be, what would change if suddenly you had a $50 incentive here, either a rebate or some way of reducing the installed cost from $100 and suddenly my net is $50, then that's a pretty good deal. my payback period is now not $100 divided by the 1440, but $100 minus 50. So I just cut the payback period in half to 3.5 years. This is a good example of why I like to keep lists of projects that are perhaps not as attractive, like a 6.9-year payback, but every 6 months or so check in with the utility, tax credits, Energy Trust of Oregon. Gee, suddenly it pops up a rebate. It could totally change whether or not this project gets done. So I like a list of projects and then checking in every once in a while. Again, electricity rates could change, rebates could change. The price of the equipment might be reduced, and now it's only $80 difference. So just because a project is no, doesn't mean never. Keep that project alive, keep checking in. I had one person after one of our full half-day seminars talk about that they were going to assign somebody in the facility to monitor that, and every 6 months kind of report in what was going on out there. And I thought that was a really good idea. Another interesting example, I'll go back to the purchasing managers here. In fact, this is a case where I was in a Safeway store. I saw 2 bulbs on the shelf, and I went, aha. Being an instructor, I like examples real live. And one of them was $4, and the other one was $5. Exactly the same wattage, exactly the same amount of lumens. Light is measured in lumens, not watts. And so I said, I'll bet I know the reason, and picked up the boxes and read the labels. Now, this is interesting because many people will read the labels on every food item they buy. They want to know what's in it, gluten-free, lactose, and I mean, there's all kinds of reasons to read labels. In the energy business, read the labels. In this case, one was rated at 8,000 hours of life, and the other one was rated at 12,000 hours of life. That's a pretty big difference. Well, one way to look at that is, for an extra $1, I got half of a bulb. I got another 4,000 hours worth of light out of that bulb. Now, if you're asked to purchase 100 of them, which CFL would you purchase? So take a guess here. What do you think the economics, if you run the numbers, work out? Now, I see that Chuck would love to buy the more expensive bulb, and Chuck is all alone.
Just to remind people, the arrow tool is right above the M of math there on your slide.
I like this group of people here today. They all would buy the more expensive bulb. Now, that might have been intuitive, but if you're trying to convince your boss or the purchasing manager of why they would spend $1 more per bulb for 100 bulbs, I will show you the math. So let's look at the math. You have a $4 bulb on the left, and you have a $5 bulb on the right. One way to look at that is at 10 hours a day for 365 days a year, assuming it's on all the time, every day. Not all the time, on 10 hours a day, but every day. That's 3,650 hours. The bulb is going to last on average 8,000. If you do your math, that's 2.2 years before you have to replace that bulb. If you buy the $5 bulb and do the math, it will last you 3.3 years. So another way to quantify and express it to someone you're trying to influence is this bulb will last more than a year longer than the other bulb. Again, I had a business manager remind me that in commercial markets, if you take your fluorescent tubes in your bulbs, you have to recycle them, and it usually is a cost to do that. And so you just postpone your recycling cost a year further out into the future. A finance person might say, well, how do I look at these, calculate a number of savings? Well, over the next 6.6 years, you would spend $400 3 times. You'd have to buy 3 batches of these bulbs for bulb A, but you'd only have to buy 2 batches of the $100 bulb. So 3 batches at $400 is $1,200. 2 batches of the bulb B would be $1,000. You'd save $200 by this decision. So whether it's the postponing the recycling costs, it's an extra year of light, or it's saving $200, there's several things you can use to convince purchasing managers that pay attention to the life of the equipment is another very important factor on looking at equipment purchases. Once you've made the purchase, the only thing you can control is the hours. You've locked in the middle part of the acronym, the W. The last thing I'd like to leave you with is if you do start tracking and monitoring and measuring electricity, and we have some courses on monitoring energy with software, but the simplest form is to look at a chart. A lot of people really like data, and they show me a spreadsheet, and I go, oh, I'm overwhelmed, too much data. But if you graph it, you can really come up with a pretty convincing demonstration of what happens when you do efficiency, or what should happen. So in this case, we have 4 years worth of information. And in the Northwest, clearly our biggest months are going to be December, January, because that's when the heating load comes in. We don't have a big air conditioning load in the Northwest. So I moved the chart instead of January through December to look at the whole winter. So what I have here is 4 winters of information. Again, you can imagine a spreadsheet of 4 rows and 12 columns. And obviously something happened here. The 2 older winters are very high. So I had some high winter bills here. And then suddenly I had 2 winters that had lower peak bills. And those were the later, the 2005 and 6 and the 2006 and 7 years. And a piece of equipment got changed. They went from a heating system that was average efficiency to a heating system that was very high efficiency. And they had about a 40% reduction in the winter bills. The graph really highlights that, I think, a lot better than the spreadsheet. So when you do start monitoring and measuring, using graphs can be very powerful, even if it's a monthly type bill. You can ask questions from charts. What changed and why? Obviously, if this was the reverse and suddenly you hadn't done any changes, but the bill went up, you can still look at this chart very quickly and go, what changed and why? And you'll have a relatively narrow point of something changed in this time period. And then you, I call it CSI at PGE or CSI at your company. You're the crime scene investigator trying to figure out what happened. Charts and graphs can really start to hone in on asking some smart questions. If you have an energy management system, or if you're a customer of Portland General Electric, we now have digital meters on all our customers, residential, commercial, industrial, and you can get an hourly picture of your energy use. So in this case, this happens to be a school building. When I first looked at this, I got overwhelmed, but it didn't take me very long with very little discussion to understand it. This is 30 days on top of each other. So noon is in the middle. Midnight is at the left and right-hand sides of this chart, and it is 30-day billing period every, I believe this is every 15 minutes, so this is a very fine gradation. And what you've got is, let's see, I'll use this tool. Up here, these are all the weekdays, Mondays through Fridays, one on top of the other. So you can see at a school, pretty logical. Early in the morning, people start showing up. The heating systems start cranking up. The lights go on, and by 8 o'clock, everything's working real hard. And then about 2, 3, 4 o'clock, things start falling off. And then finally, you're back to midnight over on the right-hand side. If you have your Sundays, there are about 4 Sundays right in here. And then here's 4 Saturdays. So I said, oh, that makes sense. And then you've got some strange things going on here, and that could be a holiday or something where the school isn't being occupied so much. So suddenly you have a graph that can be telling a story. And it's a great way to ask questions without knowing a lot of the technicalities if you're measuring kilowatt hours. In this case, the kW on the left. So one of the questions the school had was, why so long to drop off? Why, if people are gone, why is this still a lot of energy use? And in fact, they found out it was the janitorial service that came in every night. What they were doing is they turn all the lights on in the building, and as they finished cleaning a room, when they left, they would turn them off. And so that was their way of keeping track of what rooms had been cleaned. Obviously, when you look at the graph, you went, wow, that's not what I want. I'd rather have something that they turn all the lights on only in the rooms they're cleaning rather than turn them off as they leave. And that would change the shape to something that looked more like this, which is something you'd want. And you're going to save all this energy in here. You can cut that off. So you can use the graph to ask a good question, make a change, and then measure, did I see a change in that shape or not? Very powerful stuff. The other thing they could ask from this is what ran all night long. Every night, every day, at about between 1 and 2 o'clock, something would come on and stay on. And they asked these questions, and no one had an answer. No one had an answer. Facilities didn't know. And finally, someone in the IT department piped up and said, I think I know. We bought some software that turns on all the computers and backs them up every night when no one's here. What a great idea. How long does that take? About an hour. Why didn't they go off? He said the software was a really good deal and it can turn them on, but it can't turn them off. So they decided that they were going to spend some money on the more expensive software that could also turn them off. And again, that should change the shape to where about 2 o'clock, this should drop back down and come over here. And you could save the energy in this area. I did not get a response. Well, actually, I did. They think they know. Of what was going on, why are Sundays higher than Saturdays? And the answer was, again, they're trying their darndest to get some money to support the school, and they were renting out the facility for a church group to meet on Sundays. Well, now you have a way of telling the church group, gee, what do you charge for that? Well, if you take the difference between the Sundays and the Saturdays, you could actually measure what is the cost of having that group in there, and am I collecting enough money to pay for that incremental energy bill? So those are 3 good examples of what you can do with the shape of things. Without knowing much about the technology, ask smart questions. And a lot of them can lead to process changes that can help you reduce your energy bills. So that's a fun chart. There we go. So what am I suggesting you do with all this new math that you found, either as a refresher or first-time learning? There are 3 ways you can use these kinds of simple formulas. Starting with changing the behavior. That's the hour. Don't waste energy. We've got the simple picture there of the light switch. You can control the H through controlling behavior. Change the process. We looked at a couple things, for example, the janitorial that said change your process, change your procedures, and you can reduce costs. And finally, when you change the equipment, watch out for the efficiency and watch out for the life. We saw that example of the 12,000-hour bulbs rather than the 8,000-hour bulbs. Think of things you can do like put labels on equipment. I had one person tell me right next to the switch for particular pieces of equipment, they put what the KW rating was and the price of every hour this piece of equipment's used, it costs you so much per hour. And that helped people understand, oh boy, once I'm done, I'm going to turn this off. The best example I have of process change was a manager looked at that shape that I showed you before and couldn't figure out why in the middle of the night they had this pretty big spike, and it was a light manufacturing, and they found that the janitorial service was cleaning the floors by using compressed air instead of sweeping. And again, that was fine with them. They don't pay the electric bill. But negotiated a change there saying, we need to do something about the way that you're doing this. So behavior, process, and equipment. So what would I think the next steps are with the tools? Look at some kind of management feedback process, not just measure and monitor, but how are you going to communicate that to people, whether it's the people using it or the management that makes decisions or the purchasing department. Compare the energy with the benchmark. There are industry standards. We've got lots of people here who can tell you here is the average energy per square foot for a restaurant or light manufacturing or a particular industry. I think the food processing industry says what is an average energy per pound of food processed. So there are industry standards. If you don't have that, then at least say what is the history of your own energy use. Again, if suddenly something spikes compared to your own building the same month last year, you can say what changed between then and now. Use your own facility as your benchmark. The list of projects we talked about before, just because they don't pencil out right now, you could have incentives, price changes, rate changes. Keep your list of project ideas alive. Keep it going. And finally, stay abreast. Technology changes, energy price changes. Don't just do it once and forget it. Check in on a regular basis of what's going on out there. And lastly, PGE, the Energy Trust, here locally, but local utilities love to have people call. And we've got Paula Conway here. You can start with Paula. She has people. We have staff of engineer, lighting specialists, green building specialists, or you can email to that energy.consultation. For industrial customers, John Maloney. We have a staff of mechanical engineers here who are very experienced in industrial process. And their phone numbers are there as well. So reach out, ask. There are lots of people in the industry that want to help customers. So with that, I think I'm turning it back to Beth. Oh, I'm sorry, there's one more slide.
Nope, that's my slide, John. Thank you, John. We want to remind you of the upcoming webinars and seminars we have coming up here. You can visit our website, energyeducationcenter.com, to find out more. But briefly, we have 3 upcoming webinars, Understanding LEDs, Intro to Ammonia Refrigeration, and Intro to Solar Thermal and Photovoltaic Systems. One very interesting seminar that we wanted to mention to you that's coming up is Strategic Energy Management Workshop, February 27th in Salem and 28th in Portland, and that's a very good follow-on to today's webinar. Before we proceed to the question and answer portion of our webinar, I'd like to remind everyone that you can continue to submit questions to me through chat, and I will ask them of John. Within a few days, we'll send you a follow-up email with a recording of the session and the PDF of the materials. Right now, I'd like to draw everyone's attention to the poll that should have just opened up, just appeared on your screen in the lower right-hand corner. Please take a few minutes to complete the survey, this poll. During question and answer, we really value your feedback, and we do use it to improve our future webinars. And now for the question and answer portion of the webinar. John, our first question is, where do you find equipment rating information when equipment is not labeled with it?
Information. The Oregon Office of Energy or any state energy office often have listings. Energy Star websites have listings. And also, again, check with your local utility or the Energy Trust. There are probably people on staff that can help with that. If the label's not there, then you have to reach out. There's no single source. If it's refrigeration, it's a different place than if it's motors, than if it's air conditioning. So I would say use those experts. There are energy experts out there ready to go, and they know where stuff is. And if worst case, again, they could come out and measure perhaps and get a handle on the rating once they see it. Our engineers, we've got people that have been here for 20 years working out in the field, so they may be able to walk up and go, oh, I haven't seen a Franklin in years, and be able to tell you exactly about that equipment.
Great, thanks, John. And our next question is, what are some examples of larger commercial facilities, like an office building? Excuse me, I'm reading this question incorrectly here. Let me start over again. What are some examples of a larger commercial I'm thinking a commercial facility that is an office building with 60,000 square foot and 125 full-time employees. I think the question is what types of facilities would have this sort of situation?
Well, any downtown area of any major city is going to have tall, large office buildings. Schools have campuses. Large facilities like here in Portland, we have Nikes and Solar Worlds. You're going to find lots of, even though you find industrial process, you're still going to find lots of large buildings full of people. Anytime I hear buildings and people, you're going to see, we have nice pie charts back to the industry standards. You can compare your building and your industry to the standards and go, oh, look, we have a lot more electricity per square foot or natural gas per square foot or lots of different resources. So again, I would look to make the phone call to those two people on our previous slide and ask those questions. But if you're going to be in an office building, you're going to see HVAC, heating, ventilating, and air conditioning, and you're going to see lighting. And then thirdly, you're going to see lots and lots of equipment, computers, and just all Xerox machines and printers. Lots of opportunities there.
Thanks, John. And so far, this is my last question, but I encourage people to submit additional questions. How is a payback period in years converted to a return on investment?
I get this question a lot. ROI, or return on investment. In a simple form, you just invert them. Instead of taking $100 in our example and dividing by 1440, you take 1440 and divide by 100 and say, oh, if I take 14.4 divided by 100, I'm going to get about 14% return on investment. And in a simple form, that is correct. In a more complex form, it is not used a lot without doing present value type calculations, internal rate of return, net present value. But it is a simple way of saying, oh, this is a 14% return on my investment. That's better than I can get in the stock market. What it doesn't take into consideration is the time value of money over the 10 to 15 to 20 years of the equipment. But it's simply the it's the inversion of payback period. So 5-year payback period would be 20%.
Great. We have one more question that just came in. Are there resources or websites where you can find what the best rated equipment is for motors or pumps, whatever it is you're looking for?
Again, the websites I would use are for appliances. Energy Star has a great website, federal agency. I would go to, if your state like Oregon has tax credits, it's going to have a list of equipment. And boy, if it's listed there for tax credits, it's going to be high efficiency. And I would check in with the Energy Trust of Oregon website, has some really good information. But again, that question really is different websites in different places for different kinds of equipment.
Thanks, John. That was the last question. I just wanted to remind people again, all of our webinars are free and open to anyone in the Pacific Northwest. Our seminars are free to PGE customers, and there are some potential fees that might apply to outside that region.
Since that question's been asked about 3 times, I think we can very quickly come up with a simple list of websites and maybe include it in our materials. So I'll do some asking around the office and get some people some places to start for that. That's a good question, and it's come up several times.
Great. Definitely make sure we include that in the follow-up materials today. So thank you, everybody. We'll stay online for a while in case any of you would like to ask any additional questions. But thank you again. Hope to see you at a webinar in the future.